write the program which optimizes an integer linear program. But to do that, we will first implement the simplex algorithm to optimize a linear program. I mean, without the constraint that the variables should be integers. So what we have is a so-called objective function, which is a linear function. And we have a region. And we want to find the coordinates which maximizes this function. In addition to these lines that limit the region, we also say that the x variables should be non-negative. Okay, and the x variables that we start with, they are called decision variables. An example of a linear program, which was one of the first classic examples, is to have the x variable, the decision variables to be different food products, and we want to minimize the cost of getting sufficient nutrition. So that's one example. And this is of course used extremely a lot in industry and other places. So the example we had can be described as follows. This is the linear function, the objective function, and this is the system of linear inequalities that describe the region. We always have less than equal, and actually when you read the input you will only read numbers. You will not read any special characters such as equals or max or z or less than equal or anything like that. So we therefore we always use less than equal, and if our problem if we want to use greater than equal, it's easy of course to rewrite it to instead use less than equal. So we start with this, which is easier to describe using vectors and a matrix. So the first thing that you should read is the number of decision variables and the number of linear inequalities. And then you should read the vector and matrix. The vectors and matrix. These linear inequalities, they describe half planes in n dimensions. And the intersection of these half planes describe the feasible region. Okay, so all the feasible solutions, they should be within this region. And where half planes intersect, it's called a vertex, such as here. Or here, or here. Well, there as well. Okay, and the linear program, it can be either of three things. Either it's infeasible when this region is empty, or the linear program can be unbounded when there is no finite solution. It is not necessarily the case that the linear program is unbounded just because the region is unbounded. We can have an unbounded region. I mean, it would be not limited, so it would be unbounded, and with a certain objective function, the maximum value can still be finite. I mean, if it's lower values when we move away from Origo, for instance. Okay, and what we will have is, what we look for is feasible program, which means that we can find an optimal solution. And there can be multiple optimal solutions. But it's sufficient to find just one. Okay, now we will come to two important parts which we will not prove in this course. First, z of x is the value of the objective function at a certain point. And this point is a local optimum if all nearby points are less than or equal to z. Okay, so that's a local optimum. The important thing is that a local optimum for a linear program is also a global optimum. Okay, that means if we come to a local optimum, we can stop. So now the question is, where should we find the local optimums? Should we go through everything here? Then it will take some time. But the next theorem is also very nice. Namely, that if we have a bounded feasible linear program with a feasible region, then we can find the optimal solution in a vertex. That means it's sufficient to check only the vertices and take the best one. So these theorems we will not prove, but they will become quite clear when you work with this with pen and paper and also the computer and think about this. Possibly you have already studied this in other courses. Okay, so what should we do? Should we check all the vertices and just take the best one? In this very tiny example, that's obviously possible, but there can be very large linear programs which would make it absolutely impossible to check all the vertices. There can be hundreds or thousands and more decision variables and linear inequalities. Okay, I should also say that if we have such a huge system, then the algorithm that the program that we will implement will not be fast enough to solve such systems. Normal examples of linear programs, they are sparse, so that most coefficients are zeros, and then special things can be exploited so that all the computations are not done. Okay, but with the simplex algorithm, it's easy to solve systems with tens of variables and linear inequalities. Okay, but still, we still don't know how to find the optimal solution, since we don't want to check all the vertices. So what should we do? Well, one way is to start at one vertex. This one looks good. If it is in the region, that's not necessary. I mean, the region may look like this and be this part, so it's not always the case that we can start in Origo. But if we can, we do that. And then we can check which direction is most promising to go. And say we go here. Okay, and what should we do then? Then we can see if we are at the local optimum. If we are, then there is no point in going to another vertex. But say we are here, then there is certainly no idea to go back there, since we have already been there and we went here due to that one was better. So if this one is better, then we go there. And if not, this one is optimum. So say we go here, and when we come here, we will see if we should go to a neighboring vertex, and if we should not, then we are done. Okay? How to do this efficiently was given as an open problem in the 1940s at a lecture in Berkeley. And one person was late to the lecture and wrote down what was on the blackboard and thought it was a home assignment. Sometime after, he came back to the lecturer and said, okay, here is my solution. And but he complained that it was a very tough problem. So, and this is well, he got a PhD for being late, so that's not too bad.